The United Nations is a global organization that promotes international cooperation and peace among nations. It has created the 17 Sustainable Development Goals, which work towards creating a more peaceful and brighter future for the generations to come. Goal 2 is Zero Hunger, which aims to end hunger, achieve food security, improve nutrition, and promote sustainable agriculture. The objective of Target 2.1 is to ensure access by all to safe, nutritious, and sufficient food all year round. The first indicator monitors the prevalence of undernourishment, which is the percentage of the population lacking sufficient food consumption to maintain a healthy lifestyle. As of 2022, the Food and Agriculture Organization states that 9.2% of the world suffers from undernourishment. Indicator 2 utilizes the Food Insecurity Experience Scale to track the prevalence of moderate or severe food insecurity within the population. That is the percent of the population that struggles to consistently access adequate amounts of food. Currently, the Food and Agriculture Organization estimates that 29.6% of the world's food is insecure.
The consequences of undernutrition is a cyclic issue that persists throughout life. A malnourished woman is more likely to birth a low-weight baby, leading to stunting in adolescence and malnourishment as an adult. This in turn reduces productivity in the affected population and the economy. Eradicating hunger and malnutrition whilst promoting food security continues to be a huge issue globally. Developing countries within Southern Asia and Sub-Saharan Africa are the most vulnerable, due to the impacts of COVID-19, world conflict, and climate variability. Potential strategies which address these issues include boosting the nutritional value of plant-based foods, developing weather-resistant crops, and increasing local food production to reduce imports. Molecular biology is vital to the success of these strategies, with biofortification techniques like agronomic intervention, genetic engineering, and conventional plant breeding holding great promise in achieving these.
In 2017, 33 million people across Africa, Asia, Latin America, and the Caribbean consumed biofortified crops. Common examples include golden rice, zinc and iron biofortified rice, wheat, and beans. Foliar application is one method of agronomic biofortification in which mineral fertilizers are sprayed directly on crops during grain growth period, enhancing the nutritional quality of food. Nutrients can be absorbed through the cuticle, which is an extracellular layer consisting of hydrophobic lipid and hydrocarbon polymers. The stomata are pores in the surface of leaves and fruit that control the gas exchange and transpiration of the plant. Nutrients can penetrate the stomata by diffusion along the pore walls, which are less selective and less resistant than the cuticle. Foliar absorption yields rapid results and is relatively easy to implement, but is highly dependent on farmers. It is a regular activity that is susceptible to weather conditions, particularly rain, which can wash away the applied nutrients. Additionally, excess nutrient concentration can cause toxicity and interfere with other elements in the plant. Therefore, it should be used to complement other strategies for effective biofortification.
According to the FAO, in 2022, 2.4 billion people globally suffered from moderate or severe food insecurity, 80% of those residing in Asia and Africa. Within sub-Saharan Africa, drought directly impacts food security. Countries within this region have a greater risk of drought and crop loss than those in the north, resulting in a higher prevalence of food insecurity. Since these droughts can also lead to an over-reliance on food imports from Ukraine and Russia, addressing them is vital in tackling the food crisis and reducing food insecurity. One way to address these challenges is the development of genetically modified plants exhibiting drought resistance, allowing year-round cultivation of rain-dependent crops. An example of this is HB4 wheat, a transgenic species of wheat that has had the HB4 sunflower gene inserted into its genome through particle bombardment. This gene codes for a transcription factor that regulates stress response genes, thus enhancing wheat's ability to withstand water scarcity and environmental stress. Such plants can provide consistent access to energy-rich foods, reducing the dependence on imports, hence alleviating food insecurity and undernourishment within drought-affected regions.
These proposed techniques are effective in developing nutritious and drought-resistant plants, thereby contributing to ending hunger, achieving food security, and enhancing nutrition. However, it's important to note that the growing of genetically modified crops like HB4 wheat is not legally permitted in many countries and may be expensive. Nigeria and Australia have recently approved the importation of this wheat, but for broader adoption of the practices, further research regarding the safety and long-term costs associated with their use is required in order to make substantial progress towards the goal of ending hunger.